Good morning to you, or afternoon, or evening too. Good morning, good morning. I know I still sound horrible, but I'm feeling better. So hopefully I don't sound so horrible on here that you can't understand. Okay, let's talk about our next topic, which is acid and base equilibrium. All right, before we start doing that, let's do a little review, and maybe it won't be a review. Maybe it'll be, woo, that didn't make sense the first time. And so it'll be a first time topic. Let's talk about acids and bases. First of all, there are three different definitions, so we have to know which definition that we're talking about. Now, there's one called the Arrhenius, and that is very specific. By definition, an acid is something that dissolved or reacts, it makes a proton in solution. Okay, you know what? I'm going to put reacts right there because protons usually don't dissolve, they ionize. And a substance, when it's dissolved, will increase the hydroxide concentration, is your base. Okay, so that's the Arrhenius definition of an acid and a base. It's a proton donor and a hydroxide donor. All right, there's a lot of reactions out there that do not involve those two things. And so we had to go one step more generic. And the Bronsted-Lowry definition is the one that we're going to be using for the rest of the semester. But the Lewis acid is the one that we use for any reaction. All right, so the Bronsted-Lowry. The definition of an acid is a proton donor. Okay, so that's still the same. But the base is a proton acceptor, so it's not quite as limited as that hydroxide. So here's a generic reaction. So HA stands for weak acid. So an acid plus a base, the base lone pairs will actually rip off the hydrogen, and hydrogen can only have one bond, so it will give those lone pairs to the A, and it will make HB and A minus. So who's the acid? Who's the proton donor? It's this one. Who is the proton acceptor? It's that one. But we need a way to be able to look at the products because equilibrium is going to go both directions. So we're going to use the word conjugate. So if you hear the word conjugate, you're supposed to be looking on the product side. So the conjugate acid is the one that has the proton right now. So this is the conjugate acid, and this is the conjugate base. And we often talk about a conjugate acid. Yep, not that. We often talk about an acid conjugate base pair. And so in this case, it would be HA and A minus. Now, amphoteric means it can be both an acid and a base, which water, of course, is our favorite one. But generically, a Bronsted-Lowry acid is one in which you have a proton donor and a proton acceptor. The last definition is the Lewis definition, and it's very, very generic. It's going to use electrons, not protons. And every reaction that we're going to play with is going to use electrons. So an acid is an electron pair acceptor, so A. And a base is an electron pair donor. So in this case, the ammonia has the lone pair and it would donate it over to the boron. And so there would be some formal charges in here. I'm going to draw it out. All right, so this one's going to be formal charge positive and a formal charge negative. It is going to create that complex, but if you'll notice, we didn't transfer any protons. And so the Lewis acid is the acceptor, and the base is the donor. And we have other terms for those in organic chemistry, but the generic Lewis definition. But again, we're going to be using the Bronsted-Lowry definition. And before I go over to the whiteboard, I just wanted to point out water. Water is amphoteric, which means it can act as an acid or a base. And This is the perfect example for water. So let's write out the equilibrium equation for water. Hey, water plus water makes the hydronium ion and the hydroxide ion. We can shorten that to water is just going to the proton and the hydroxide, but remember, protons don't just float around. It's always the hydronium ion. And so water is acting both as the acid and the base. So this one's the conjugate acid, and that one is the conjugate base. And that was the conjugate base. Now, before we get into the equilibrium expressions, I'm going to go over to the whiteboard. And we're just going to talk about acids and bases. All right, let's use our favorite acetic acid. Now we're not in Gen Chem 1 anymore, and so I don't have to write C2H3O2 out anymore because the acetate is not going to change. So I'm showing you, hey, the hydrogen's what I'm interested in, and the acetate's just the other piece. We're in equilibrium. Water in this case is going to be my donor of electrons, and it's going to give up its lone pair to the acetate. So I'm going to be left with H3O plus. And you'll notice I'm going to start leaving off the phase labels too, because all of this equilibrium's in aqueous conditions, so I tend to start leaving it off. If in doubt, never leave it out. Okay, so there is my equilibrium equation. Definitions. What in the world am I looking for here? Now, I did notice I was playing with a proton, so this is probably an acid. Well, which acid am I playing with? All right, Arrhenius. Wow, I can't remember how to spell Arrhenius's name. So we're going to just put Arrhenius acid. Hey, okay. So Arrhenius acid is a proton donor. So who was the proton donor? So I'm going to do this one in red. This was the Arrhenius acid. But who is the Arrhenius base? Remember, an Arrhenius base is a hydroxide donor, and there's no hydroxide in here at all. And so that's a limiting factor. So I don't want to use the Arrhenius definition. I'm going to go to the Bronsted-Lowry. So the Bronsted-Lowry acid and the Bronsted-Lowry base. This one is the proton donor. This one is the proton acceptor. Oh, who's the donor? This one is the Bronsted-Lowry acid. Who accepted it? This is the Bronsted-Lowry base. And then if we're looking on the other side, this one would be the conjugate acid, and this one would be the conjugate base. Well, let's see if we can put our Lewis definition on here too. All right, so Lewis acid is an electron pair acceptor. So who accepted the lone pair? Or sometimes for Lewis's, I like to think of it the other way, an electron pair donor. Sometimes it's easier for me to pick out the base. All right, who gave up its electrons? Oh, it was the water. So this is the Lewis base. So that makes this one the Lewis acid because it accepted the lone pair. So again, all the definitions have their purpose, but we're going to be using the Bronsted-Lowry. And then later on, we will switch over to this Lewis acid, Lewis base. But for right now. Okay, let's delete the bottom part. Right, we have a balanced chemical equation. I just want to show you that we can still put it into an equilibrium expression. So K is equal to the products raised to their coefficients over the reactants. Water does not go in. So there is your equilibrium expression. And then we ask, can I find K? And the answer in this case is yes. So if this is an acid, this reaction is called acid ionization. Because remember, acids are molecular and they react with water to make ions. They don't just dissolve, they react with water. Acid ionization equilibrium constants are K subscript A. So because I know this is an acid ionization, I should be able to find a K subscript A as long as it's under the right temperature. And remember, if I don't give you a temperature, it's going to be 25 degrees. So if you're looking at your reference sheets, we're going to go and find acetic acid, and its K value is 1.8 times 10 to the minus fifth. Now it is less than 1, so I know that reactants are favored. Which isn't surprise because this is a weak acid. And weak acids, they don't like to react very much, okay? All right, so there's a generic for that weak acid. Now I'm going to go back to the water. Because guess what? Water is also a weak acid. Okay, I'm going to use a shortcut. Never use a shortcut unless you understand why it works. Okay, so I'm not going to put the other water in there. Oh, look, there's my balanced equilibrium equation. K is equal to the products over the reactants, but water does not appear in an equilibrium expression, so that's the whole thing. Then I ask myself, can I find that K? Now, if this is water at around 25 degrees, it's very special. It has a little subscript W, and KW is 1 times 10 to the minus 14th. That is on your reference sheet. It's on the green pages. All right, 1 times 10 to the minus 14th, it's sig figless. Well, I'm having a hard time spelling today, aren't I? So you can put 1.000 as many as you need. Oh, look at this. So 1 times 10 to the minus 14th is equal to the proton concentration and the hydroxide concentration. So if it's at perfect equilibrium, okay, if it's at perfect equilibrium, it would be the proton would be the same as the hydroxide, and that would be 1 times 10 to the minus 7th molar, okay, as long as they were equal. And so water is a very unique thing because it's going to give us this constant, this Kw constant, and it's going to give us something called pH and pOH, but that is for a different lecture. All right, let me go back. All right, we've seen our definition of Arrhenius. We've seen Bronsted-Lowry. We've seen the Lewis. I just did the water for you, so here's the equilibrium expression. There's the Kw again. It is on your reference sheet. And then we're going to use these terms neutral, acidic, and basic. Neutral means they're equal, okay? So 1.0 times 10 to the minus 7th. Acidic means the protons are higher in concentration than the hydroxides. And so that would be acidic, is when the protons are more than, if you will, the hydroxides. So that's acidic. And this pH is going to come in useful when we start talking about this. And then basic would be the other way around. All right, there is our introduction to acids. Again, do we have to use all the definitions? No, but we do need to understand what they are and their purpose because they will crop up now and again and help us understand things. And then we will go on and plug in our numbers just into the ice tables like basic equilibrium. But until next time, Jolly out.